Yang, and also with CP, with Omnip from Naval Postgraduate School in NTU. So pretty much, if you look at this Typhoon Morakot, it's heavy precipitation, but also there's the whole village being wiped out with the cost of hundreds of lives. It's a very tragedy, and it's a very big event in Taiwan. And if you look at this, surely it's a big trough, as mentioned by Huang Xiongxu yesterday, and also a huge southwesterly, and you can see a rain band, all these things. So it looks like it's pretty multiple scale feature associated with this. And it's not just the long duration, but if you look at this, this is a CloudSat cross-section from a CloudSat website. This is Taiwan, and you can see a very powerful precipitation machine, big convections and pouring rains. So it's a very strong. And then this is from some of the Tai Chi's work, very long duration precipitation and the interesting rain band structures. So it looks like it's saying a lot of this tremendous rain caused by slow movement of the Typhoon Morakot. So it gives you a long duration time. But the long duration time is one thing. You still need some powerful machine to put out the rain. So some mesoscale convection developed. But you have something very significant developing. You also need some water vapor supply, which is possibly coming from the southwest monsoon surge. And this southwest monsoon surge also gives the asymmetries in the convections. And surely people talk about this the terrain and other things. So it looks like these things are important. So what we did was thinking about how unprecedented of this Typhoon Morakot is compared to this the local history in Taiwan. So what we did actually was looking at here, the translation speed is a linear translation speed. So we're looking at this arrival point of a typhoon, landfall point, and then the departure point, and then take a straight line divided by the duration time. So this is how this translation speed is calculated. And here is just some cumulative rain from the Central Weather Bureau stations. So as you see from here that the number one actually is the Typhoon Nari. It's a very causing the Taipei flooded Taipei City, and all the MRT, the subway station being flooded. It's with something like a 9,000 millimeters. And Morakot of this one is the second one. And surely there are many other famous Taiwan like Jemi, Talim, Kameji, Sindaku, and Haitown, and a whole bunch of these typhoons pointed out here. And in here, so you can see that as the translation speed gets lower, surely all this, I think a lot of needs to be very watched for this heavy rain. But on the other hand, if you, even with a very low translation speed, still there's a big varieties of the variation in the precipitations. And for example, this, and as far as the disaster goes, it's maybe good. This one is called Tremi. It looks pretty weak, and the total amount is not that much. It's low duration. But this one is dumping this 500 millimeter rain in 3 hours in Kaohsiung City. So it's caused a tremendous damage. And this one, Litima, we'll see later, it's a very long duration time. So it's causing the rain pretty high, but actually it's the average, if you average per hour wise, it's not rain that much. So we have a bunch of this. And also in here, the one showing the blue color is the storms after year 2000. So you can see if you look at the ranking here, it looks like something happened drastically after year 2000. So this is about the translation speed. And then we look at this, all the typhoons, because we have, we can look at this is the translation speed before, and in here, this speed is the make a landfall So we see that looks like all the typhoon in the past, once it approaching Taiwan, before make a landfall, the speed slightly increase a little bit. And then it drops. So this is a mean, and this is the standard deviation. But the point here is that during the landfall translation speed, there's a very large variabilities that's coming to here. So you cannot simply attribute to, well, because of the stream flow is weak, it's coming so slow. Surely it's possible, but still looks like something happened due to the terrain. So here are just some examples. The open, we see the typhoon, it's once close to Taiwan shows a cyclonic path. So one hypothesis may be because of the topography stretching, causing some vorticity here and causing additional stream flow. And sometimes the typhoon, before they make a landfall, they make this kind of loop. And that's also for forecasters a very difficult problem. So with that similar time and the translation speed, so what I did plot here is all this, the ranks with the high precipitations of the typhoon. So this is kind of spaghetti diagram, but anyway, the whole point here is this bottom one is a Morakot. So Morakot is really a very low one, and the Taichi mentioned this morning about this one is 4 times faster, but actually this one is also, after you leave the Taiwan, it drops. But the Morakot is also so unique in the way that most of these heavy rain typhoons, after they leave Taiwan, they resume their speed. But Typhoon Morakot appear to be still in a very low speed. So this is quite unique part. And also showing this figure, it looks like most of these major things is coming